In the last video, we went over valence bond theory and how we use it to explain how bonding happens within molecules. And so the idea is that we're now using our knowledge of orbitals and regions of probability to explain what's happening during bonding. For example, we saw when the H2 molecule forms, you have an overlap between the single electron in the 1s of H and a single electron in the 1s of another H, overlapping together. So those two orbitals will be overlapping for maximum stability. There's overlapping that occurs, and within that region of overlap, there's only two electrons allowed with opposite spins, of course. Here we have a molecule of HF where the single electron in the 2p from fluorine, because most of them are paired except for the one electron at the very end there, will bond with the single electron in the 1s from hydrogen, and there's a region of overlap over here. So the s orbital is overlapping with the 2p orbital of the fluorine here. And then over here we have two fluorines, both their 2p orbitals are overlapping over here to create a bond that we see here. So you should be able to explain bonding using valence bond theory. So let's say, for example, you're asked to describe the bonding in H2S using valence bond theory. The first thing I want you to do is to draw a Lewis structure, because the idea is that whatever you explain using valence bond theory should match the Lewis structure. So you draw a Lewis structure for H2S, which looks like this over here. We're going to draw energy level diagrams for all the atoms involved in this bonding. So we have H2 and S. We have two H's, which are drawn here, and then the S's, and the S is drawn over here. And then I have the energy arrow pointing up. And so we'll draw in our single electrons for a hydrogen, and also we're going to draw in our energy level diagram for our sulfur. And so what I want you to notice is that we're going to explain bonding as it happens using valence bond theory. So regions of overlap, we have a connection between hydrogen and sulfur. So this hydrogen has a single electron here, and the sulfur has a single electron here. So we know for sure that this is probably going to overlap with this. And then we also have another single electron here, will likely overlap with this one, this hydrogen over here, which has a single electron to make this bond here. We also have to explain the lone pairs, and the lone pairs can be explained by the fact that you have in the valence shell the 3s electrons here and the 3p electrons here that are paired, and that corresponds to these over here. So what we did there is we just explained valence bond theory, explained the bonding in hydrogen sulfide using valence bond theory. And we could draw a little diagram like this to show the overlap that's happening. Little circles or spheres to represent the hydrogen electron overlap with the 3p1 orbital of the sulfur, and then over here another 3p orbital of the sulfur overlapping with another hydrogen, and that there shows what the bonding would look like. And this creates a bent structure overall. So this is our drawing using orbital level diagrams. So we don't show all the orbitals, we're just showing the ones we're interested in. This H overlapping over here with the single electron from the sulfur in the 3p, and this H overlapping over here with the other single electron from the sulfur in the 3p to get this overlap over here. And so you can do a similar process with pH3. So again, you draw your Lewis structure first. Make sure that you draw energy level diagrams for all of the atoms involved. So you'll notice that we're drawing 3 hydrogens over here. And we're also filling out the orbital level diagram, energy level diagram for phosphorus. And so notice that each hydrogen is connecting once to the phosphorus. So this hydrogen may connect to this lone electron here. So there might be some overlap with the 3p and the 1s over here. There'll be some overlap with the 1s and the 3p over here, and overlap with the 3p and the 1s over here. I might have done it in different orders, but the point is that this single one will interact with one of these. This single one will interact with the remaining, and this single one will overlap with the last one. So you can see all the interactions in red there, and you can see that they're going to overlap with their hydrogens over here, as you see. You also have to be able to explain the lone pair. The lone pair on the phosphorus comes from this 3s electron over here, or these 3s electrons over here, which are part of the valence shell, right on the phosphorus over there. And so notice that our energy level diagrams match our Lewis structure. And so you can do that for a variety of different molecules. You should be able to draw it out as well. Oftentimes, just to shorten things up, you don't have to show all the non-valence electrons or the core electrons. You can leave those out. So for example, if you had just made a ... the ellipses, and left this out and just included the valence electrons, that would have been acceptable as well, just to shorten how much work you have to do in your drawing. So we'll do another example together to show you how I'd want you to do it if you were handwriting this, because you won't always be having these fancy animations. So let's go ahead and do that for BrCl. So we're going to explain the bonding in BrCl using the valence bond theory. So what we want to do is we want to draw an energy level diagram for each of these. And we also want to do a Lewis structure for this. So generally, we start off with a Lewis structure. We have BrCl, and then you'll have the electrons that surround it. They're lone pairs, but we really have the single bond in there. And so we know there's a region of overlap happening here. We just want to show what that region of overlap is. So we're going to make an energy level diagram for chlorine and then energy level diagram for bromine. And we'll go ahead and do that, make our arrow over here to show energy going up. And we'll make our arrow over here to see energy going up. I'm just going to draw in the valence electrons because they're the ones involved in bonding. So I'll go to my periodic table. We'll start with chlorine. It looks like chlorine will have so 3s2 and then 3p1, 2, 3, 4, 5. 3s2, 3s2, 3p5. And so we'll go ahead and do that. We'll put our ... to show we're kind of ignoring the core electrons and we're focusing on the valence. So this is our 3s, and then our 3p's are over here. Whoops, there's only 5 in there. And we also have bromine. So let's go take a look at bromine, what its valence shell looks like. So bromine's all the way over here. So it looks like we have 4s2, 3d10, and then 4p1, 2. So 4s2 and 4p5. Those are the valence electrons for a p block element. 4s2, 4p5. And it makes sense. It's just one period below, so obviously an energy level higher. So I'm only going to focus on the valence electrons. So we have our 4s over here. I'm not really going to focus on the d orbitals right now because those are not the electrons participating in the bond since it's p block. We really want to focus on the valence electrons. So here we have it. We can take a look at where the bonding will happen. We can see that the region of overlap will be where the single electrons are, so here and here, and that will be responsible for creating the single bond over here. So this single bond results from overlap between 3p of bromine and 4p of bromine. And what I meant there was obviously chlorine here. So it's the 3p of chlorine and the 4p of bromine. And so that's the region of overlap responsible for that. And for the lone pairs, so if we choose a different color here, you'll notice chlorine has some lone pairs on it. These are lone pairs, lone pairs, lone pairs. Those lone pairs can be represented there. And I circled the wrong one. Let me just redo that. Looked at my bromine diagram by accident, but it's very similar. For chlorine, these are the lone pairs. And for bromine, we have them here, here, and here, which are represented here, here, and here. So you can also explain your lone pairs. So you can say that so this is our first point, lone pairs in bromine can be found in 4s and 2p orbitals, and specifically it's the x and y ones. And then lone pairs in chlorine can be found in 3s and 3p orbitals, specifically the x and y ones. So we've just explained bonding using the energy level diagrams and orbitals. The last thing we really need to do is we need to draw what this looks like. And we don't have to do a fancy drawing. In fact, we can just focus on drawing just one segment of the P. Doesn't really matter which one, with an electron in it. So we'll say that this one here is from chlorine. And then we can make a similar region of overlap over here. We can make it a bit larger just because it's higher up in energy for bromine. And the other electron would have an opposite spin, and this one is from bromine here. So we can call this one here would be the 3pz from chlorine, and this one here would be the 4pz from bromine. And it's this region of overlap that's responsible for the single bond. Keep in mind, the other orbitals are still present. I'm just choosing to focus on this drawing specifically. So what do we do in this drawing here? We explain the bonding that happens in BRCl using valence bond theory. We essentially drew a Lewis structure for the BRCl molecule. We drew energy level diagrams where we only focused on the valence electrons because those are the ones that are participating in the bonds and that we see in these Lewis structures here. We explained that the bond came from an overlap between the 3p single electron here of chlorine and the 4p single electron here of bromine. And it's this overlap specifically that leads to that single bond. And then we showed that the lone pairs from bromine come from the 4p full filled orbitals here, the two of them here, and the 4s. And then from chlorine in a similar way, but in the 3p and 3s, that's where their lone pairs come from, or its lone pairs come from. And then we did a simple drawing of orbital overlap happening here, just to show that that's the single bond that's forming there. And this forms a linear shape for the molecule overall, just as you would see in VSEPR. And this is a linear molecule. So that there was another example of using valence bond theory to explain bonding. I do need to make sure that you practice these concepts, being able to draw this and explain what's happening with the animation and without. So if I were you, what I would do is I would try to read the question, describe the bonding of H2S using valence bond theory, try to draw it out yourself, and then come and take a look at the animation to see if you were able to explain it and show where all the different pieces connect. In the next video, we're going to focus on the strengths and weaknesses of the valence bond theory. We're going to be looking at a new concept added on top of this called hybridization. So valence bond theory is a really good theory to explain bond angles and shapes, and it uses orbitals. It incorporates quantum mechanics into shapes, which is great. It's an awesome strength. But the problem is that valence bond theory doesn't always explain all the observed bond angles that we would expect to see. In some situations, when we use valence bond theory, the way we draw it and the way the orbitals overlap, the angles don't end up being where they should be. So if you were looking at the example of water, water has a bond angle of 105 degrees, or 104.5 approximately. But if you use valence bond theory and you show the orbital overlapping, when you do modeling, you get 90-degree bond angle, which doesn't match up with what water is actually supposed to be. So there needs to be some other explanation for how the bond angles arise. So if we look at this situation here that we saw with H2S, valence bond theory was fine explaining H2S. It gave you the proper angles. In the end, the models predict the proper angles that you would get if you were using VSEPR. But for other molecules, like water, for example, that I just mentioned, the bond angles don't quite work out. And the other problem with valence bond theory is it doesn't always properly explain how bonding can occur or where bonding can occur. Some things seem a little bit off. So for example, if we look over here, if we look at carbon and we draw its energy level diagram, remember I said that bonding really needs to happen where you have single electrons. And then you can have other electrons combine and pair with those single electrons. So if you look at carbon, you'll notice that it only has two single electrons here. So if we just stick with valence bond theory the way it is with these energy level diagrams, it looks like carbon can only really bond in two places, here and here. But in reality, we know carbon forms 4 bonds and can accommodate more electrons than just 2. So how do we explain why carbon can form 4 bonds rather than 2 using valence bond theory? Well, as is, we can't. So what we have to do is we have to incorporate a new concept called hybridization, hybrid orbitals, and electron promotion. Once we incorporate this information into our valence bond theory, then we can explain the bonding of things like carbon. We can explain why bond angles more effectively as well that match up with our experimental results and experimental evidence. So in the next video, we're going to be focusing on the concept of hybridization, hybrid orbitals, and electron promotion incorporated into valence bond theory.